Hello, hi everybody. Can you hear me?
Yes.
Excellent. It's really nice to meet you all. I'm very excited to speak and about the overwhelming response to the webinar. I hope I will do you justice as I talk to you about supernovae. Let me share my screen and let me see if you see my slides. Excellent. And I'm going to start presenting. So I've been working with the Rubin Observatory on the science community, side. So I am the coordinator of the LSST science collaborations. These are the team of scientists that are really excited about the beginning of the survey and think the survey can do really great science and are preparing to do that. And in particular, there are 8 science collaborations. I've also been serving as the co-chair of the Transits and Variable Stars science collaboration that specifically focuses on, you heard the 4 science theme of the Rubin Observatory. The Transits and Variable Stars science collaboration, or TVS, focuses on the transient universe, from variable stars, transiting planets in front of stars, all the way to the most distant explosions in our universe, including supernovae, which is what I'm going to talk to you about just now. So this is an image of the sky over Chile. It's a really delightful image because the site in Chile, this is the site that will host the Rubin Observatory. You have an early rendition of how we thought the building was going to look on the right. This site is an exquisite site for astronomy. It is a very high altitude. It has very clean air, which leads to very good seeing. So you can see the stars very clearly. It's a dark sky, so you don't have a lot of light pollution. And this is in the southern hemisphere, so the sky looks a little bit different than what those of us who are on the call who live in the northern hemisphere are used to. Particularly here, you see the beautiful Magellanic clouds on the left, and this dust streak in the center is our own galaxy. What you're missing from this image is that this is a static image of the sky that leads you, or may lead you to think, that the universe is a never-changing, very quiet and stable place. This is what humanity thought for literally millennia. And in fact, that couldn't be far from the truth. The sky is the site of tumultuous, continuous changes. 10 stars explode every second in the universe. If we could see them all, it would look something like that. And if we could hear them, it would sound something like that, which is reminiscent of pop current popping. And I'm stealing this image from Andy Connolly, also a Rubin Observatory, one of the main participants in the Rubin Observatory, and his TED Talk. So 10 stars explode every second in the universe. To give you just a rule of thumb, this is about 1 star per century per galaxy, and there's a lot of galaxies out there. The problem is that most of those galaxies are far away, and even though a single supernova shines about as bright as a single galaxy, we don't see the majority of those galaxies, and accordingly we don't see the majority of those supernovae. With the naked eye, seeing a supernova was, for the majority of history of humanity, an incredible experience. Seeing a new star appearing in the sky, that was really shattering our understanding of the universe. It made it into historical iconography. This is King Henry looking at a new star in 1450. On the right side, you have a scientist, Tycho Brahe, looking at a new star, which really wasn't a new star, but in fact a dying star, an exploding star, supernova, in the 1540. And even further back and outside of Western tradition, the iconography of new stars, of supernovae, made it into prehistorical depictions. And this is an indigenous population of America that depicted a star that we think is a supernova that was visible on Earth in the year 1040. Just to give you a bit of more of historical context, the first historical records of new stars in the sky that correspond to supernova as we understand it today are from the early centuries after Domini. So the first few are in the Chinese literature, because Chinese were exquisite astronomers and exquisite history takers. So supernova 185, supernova 393, these correspond to the year of the supernova. There's a bit of a gap. The next supernova in history, recorded in history, makes it in the year 1000 or so. There were 3 supernovae, 1006, 1054, the one that we think I showed you was recorded by indigenous population in the Northern Americas, and 1881. Yet later on, these supernovae begin to take the name of the scientists that discovered them: Tycho supernova and Kepler supernova in the 1600s and 1800s, and at last Cassia. I'm gonna pause here and indicate that Cassia was the sort of last one of the historical supernovae in this sense, which was discovered in the 1800s. Because in the 1800s, we began using telescopes regularly for studying astronomy, and telescopes allowed us to see a lot more supernovae. So on the left side, you have a map of the sky as it gets populated by historical supernova all the way through the modern era. And you will see in a second how much more rapid the discovery pace becomes as technology improves. Right now in the 1960s, we're using photographic plates. We're about to switch to digital photography for astronomy, which will determine an incredibly fast-paced increase of the supernovae that we discover. And here you see the name of the surveys that discover them. Also on the right-hand side is a histogram of well-observed, so supernovae that actually had spectra. And if you are confused by what a spectrum is, we'll talk about that in a second. But this gives you a sense of what surveys discover which supernova and at what rate. So you see that this growth in the supernova that we know is not linear, but it has bumps that correspond to new survey that increase the number of discoveries by a step and not just incrementally. This SDSS was one of the first digital surveys, PTF, ZTF, the Zwicky Transient Survey. These are all precursors of the Rubin Observatory LSST. The Rubin Observatory LSST, as you've heard, you can take a rule of thumb of a factor of 10 more and a factor of 10 better than any other surveys. So that discovery becomes 10 times more than the current precursor, the ZTF survey. So we do expect this map to get filled in a transformational way with the advent of the Rubin Observatory LSST. So to understand supernovae, we need to understand the lives of stars, because supernovae are the last stages of the lives of stars. In a sort of macabre way, we often call them the death throes of stars. So let me start with this children rhyme, this modification of the Twinkle Twinkle Little Star children rhyme, which I'm going to attribute to Professor Viviana Acquaviva, who's a friend of mine who works at CUNY and had a child recently, and reformatted the Twinkle Twinkle Little Star rhyme to say, twinkle twinkle little star, I'm aware of what you are. You're a glowing ball of gas. How you live depends on mass. This last statement is the crucial one. The entire life of a star is determined by the initial mass with which it's born, and only marginally by circumstances such as the environment in which it lives or whether it has siblings. This is called the HR diagram, Hertzsprung-Russell diagram. It's the way in which astrophysicists like to visualize the life of stars. You have temperature, luminosity against temperature, but because the life of the star is determined by its initial mass, each star of a particular initial mass occupies exactly one place in this diagram for most of its life, for the part of its life, which we call main sequence. And I'll get back to that in a second. So the way you want to think about it is that much like in a parallel with Hollywood stars, the biggest stars live fast, die young, and die spectacularly in spectacular explosions, which we call supernovae. Let me give you a quick understanding of what it means for stars to be in main sequence first. So stars are ball of gas. The gas, the mass of the star obviously is enormous, and it's determining pressure that pushes the star itself towards its center. So you have gravitational pressure that is pushing the gas towards its center. At the same time, you have the gravitational pressure in the center is determining nuclear reactions that generate photons that push the star material outward. So when you're in hydrostatic equilibrium, when you're in the main sequence, which is where stars spend most of their lives, you're in this state where you have gravity pushing the star in and nuclear reaction pushing the material out, which compensate each other into a state of equilibrium. Once that is over, and as you do that, you produce elements that are progressively heavier, from helium to hydrogen, calcium, oxygen, etc., up until iron. When you get to iron, though, there is no net advantage in energy in producing heavier elements. While before you were fusing elements that were heavier and producing energy, to fuse iron into heavier elements, you actually need to give it energy. So there's no net gain, which means that once the star has produced all the elements down to iron, and only the most massive stars do that, the least massive stars only end up at helium, then the core of iron collapses because it cannot produce energy to support itself against the gravity. That's when you get a supernova explosion. As I mentioned, the life of the star depends on its mass. First of all, the thing that depends on its mass is how long the life of the star is. A star like the sun lives for about 10 billion years in main sequence, and then it evolves out of the main sequence because it lacks the support of gravity and nuclear reactions. More massive stars, and they get to be as massive as 100 solar masses, live much less than 1 million years in main sequence. After that, they have a phase which is called supergiant, and then they explode into supernova. What's left over after a supernova is either a neutron star or a black hole. However, even low mass stars, and by low mass here we're talking about anything that is less than 8 solar masses, down to about the minimum mass for a star, which is 0.08 solar masses, even those stars can explode. Normally, left to their own devices, they would progress to a state that we call white dwarf, which is a state of degenerate pressure, and they will just die by cooling slowly after that. So white dwarfs are just one of the kind of remnants of stars that we have. I'm going to skip through this in the interest of time. What happens is that even if they would normally be left on their own devices, would just die by cooling down, if a white dwarf has a companion, has a sibling, which, by the way, it happens to be the majority of stars are in multiple systems, double or triple systems. If it has a companion that it's dumping mass onto it, then it will exceed a critical mass, and it will also explode into a supernova of different type. We call these thermonuclear supernova or supernova type 1a, which will then leave a neutron star as a star remnant. So I'm going to give you 3 reasons why we study supernovae. The first thing is that supernova are really what enables life in the universe. They're extreme physics laboratories, so we want to study them to understand the extreme physics conditions that are developing in the supernovae, and we're going to use them to trace the evolutionary history of the universe. First of all, this is the famous quote from Carl Sagan: "We're all made of star stuff. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pie were made in the interiors of collapsing stars." This is true because of what I told you earlier, that in the core of stars, you forge elements that are heavier and heavier. You start with hydrogen and helium, which is really all that was made during the Big Bang. And then you forge heavier and heavier elements until iron. When the iron is formed and you cannot go any further, you have the explosion. During the explosion is when you form even heavier elements. So as a result of that, the majority of the elements that we know in our universe, and the majority of the elements that we know on Earth, are either forged inside of stars during their life cycle, carbon, nitrogen, lithium, or are formed during stellar explosions or even stellar mergers. The stellar mergers will be the thing that you know, that you have heard of probably recently because they liberate gravitational waves, which we have recently been able to detect. This, by the way, the first person to understand the thermonuclear activity in supernovae were Titus Pankey. He often doesn't get credited for this, but he was a Black scientist at Howard University, and this was part of his thesis in 1962. Normally, you would see this cited about 20 years later, attributed to other scientists. So when you see a supernova remnants, this is the material that has been formed both inside of the star, so the hydrogen, the helium, the iron, as well as heavier elements like nickel that get formed during the explosion and typically are unstable and decay rapidly. And you see them as shining remnants because you see both the light from the star shining through them and reactions of decay and nuclear reaction of decay in the elements themselves. Secondly, they obviously, it's very interesting for us to understand this extreme physics environment. However, when we look at a supernova, all that we see is a tiny little dot getting bright and dim. So it's very hard to study this extreme physics with such remote probes. The way we collect data about supernovae primarily are two ways. We look at how the light of the supernova changes in time. We can do it for the whole light across the whole electromagnetic spectrum, or we can do it in colors, for example, only in the optical or only in the R filter, and comparing maybe these filters. So that tells us a lot about the nucleosynthesis that goes inside of the star. That peak that you see where the maximum brightness of the star is reached is because nickel is getting formed, and when you reached all of the nickel fusion that you can reach, then the nickel starts decaying. That's the falling part of the light curve here. Sometimes you see a very rapid rise at the beginning of the star that are interaction of the photons with the star outer layers or with the star ejecta. And by the shape of the light curve, we're able to tell in some cases what kind of star it came from. For example, a supernova type 1a has this very distinct and clear and simple light curve is a white dwarf, whereas a supernova 2p comes from a very massive star. Yet this is not a lot of information. Something that we can do to get more information is get a spectrum, except spectra are really expensive because you're looking at the star in very refined color beams, at very small beams of wavelength. And as you do that, you need to take very long observations. LSST will only look at light curves, other telescopes will look at spectra. And from the spectra, we can say what elements are formed in the star and what elements are shed out of the stars. In the interest of time, I'm going to move forward to the last point, which is that supernovae are excellent tracers of the evolution of the universe, primarily because we see them really far away. The farthest supernova that we've seen is at 10.5 billion years ago, so only 3 billion years after the Big Bang. So it's a very far away object, and it's an object that lives in a much younger universe than we do. And because it's far away, it's redshifted. So the universe is expanding, and much like the siren of an ambulance, that means that the spectrum of the supernova looks redder than it is. And we can measure how much redder, so we can measure what redshift that is. We can also measure how bright the supernova looks to us. And for this particular type of supernova, the 1As that come from the white dwarfs with companions, we know that that is entirely dependent on how long the light curve lasts. So the shape of the light curve is the same. It can be stretched, but it maintains the same height to width ratio. That is why these kind of supernovae obtained the Nobel Prize a few years back, because they allow us to see what is the redshift at a certain distance from us in the universe. So how fast was the universe expanding back in time? And this tiny deviation here from a straight line is what tells us that the universe is expanding at an accelerated rate. I know that I went a bit fast over this, but I think it's okay because I think that's tomorrow's topic for this workshop. And with that, I'm leaving you with the reasons why we study supernovae, and I want to encourage you to absolutely get in touch with me if you have any questions. Sorry for running a bit long.
Okay. Artist, you want to go ahead and pop in? I think a lot of the questions have been answered thanks to this amazing group of colleagues that we have online with us today.
So Elaine, you have no questions you'd like to ask?
Well, most have been answered by other people. Although
you guys did great. That's
awesome. Although they are talking about there is a black hole just 1,000 light years away from us. What was our solar system at one point in a binary system, or did this sun supersede our own?
I don't know if there is I don't know of any evidence that our solar system, that our sun was in a binary system. So our sun will end up, presumably, unless it captures a companion, will end up as a white dwarf, and it will end up dying slowly as opposed to exploding into a supernova. But don't get comfort in that, because in the earlier phases, it will expand its radius greatly, and it will expand its radius to well past the orbit of the Earth. So we will be engulfed by it before it becomes a white dwarf. Chances are we will have made our way into extinction in many ways before that time, though, because that's a couple of billion years in the future.
Another question that was interesting is why the huge historical breaks in observations?
So because technology advancements. So the SDSS is the Sloan Digital Sky Survey. It was sort of like that first really dense group of supernovae that you saw in the map that was getting populated at the same time. It's because this project was designed to do very much what Rubin Observatory will do with LSST, just in on a smaller portion of the sky and at a brighter limit, so it won't go as deep in the universe because the technological limitations were such that you couldn't just yet do Rubin LSST. So, but you can think about this as very much a precursor of this survey. And so we generally call these synoptic surveys. And synoptic surveys where you're trying to observe a large chunk, a large volume of the universe are great to discover supernovae because they happen everywhere, but we can only see them if we look far away and at a whole lot of galaxies. Okay. So most of those increases in data in discovery rate are connected to specific surveys.
All right, I'm gonna do one more question so we can pop a break in here for everybody. Will the Rubin data help with the R process versus S process understanding for heavy element creation?
Right, so these are all the elements that go past nickel that I didn't discuss that get created, but that get created in stars as well. So it will, in as far as, so for example, we had a breakthrough in understanding the creation of elements through these processes recently when the first counterpart of an electromagnetic, of a gravitational wave signal was detected. So a gravitational wave signal was detected by LIGO, and then a bunch of telescopes went chasing after that gravitational wave signal to find something in the electromagnetic spectrum, so something that looks kind of like a supernova, a transient, and see how it actually looked. And so Rubin will be instrumental in detecting counterparts of gravitational waves because you have a very large field of view, so you can scan the sky very rapidly. And gravitational waves, even when they're detected, you don't know exactly where they are in the sky. You know that with a very significant uncertainty. So you need telescopes that can both go very deep to see faint things and do that across large swaths of the sky rapidly. And Rubin is great for that. So it will help in as far as it will help identifying counterparts. A lot of that science, though, truly comes from taking spectra and taking observations at all wavelengths. So combining the optical with the X-ray, with the radio. So it won't be just Rubin, but Rubin will discover the counterpart, and then a bunch of other facilities will follow it up and augment the data to enable really the physical understanding.